Hi Wildcats, this is Unit 4 focus question number 2, notes overview, and we are going to talk a little bit about electric force today. So I want to start by returning to some observations that we made during electricity demo day, one of which we saw the bits of paper. When I used the plastic rod and brought it near them, they jumped off the table and were stuck to the plastic rod. We may have done the demo where I could actually curve the water using a charged plastic rod, and we definitely did the Van de Graaff generator, where the strips of paper that were taped to the side floated up in the air. So I guess my question is why? All of those relate to electric force, but why are those occurring? And so we need to look at what is electromagnetic force. Electromagnetic force, also written as F sub E, so all forces are F for force, and then we use a subscript to indicate what type of force it is. So F sub E would be the abbreviation for electric force. Like all forces, the unit for it will be newtons. Okay, so electric force occurs when charged objects exert a force on each other. So here are two positive charges. We know that like charges repel. Well, repel, they push away from each other, and a push is a force. So therefore, there must be some force causing these two objects to move away from each other, and that force is the electromagnetic force, or the electric force for now. Same thing is true with negative charges, but in opposite charges, they are pulled towards each other by some force. And what is that force? Again, electric force. So electric force is the force exerted by charged objects on other objects. And it can be attractive, like we see here with two opposite charges, or it can be repulsive. And finally, this is caused by a field force. So field force is a force that acts without the objects actually touching. So a contact force, or a non-field force, would be like if you come and push a piece of a book across the table. You have to literally come in contact with that book. Your finger has to touch the book to move it. So that would be a contact force. It requires physical contact between the two. However, these charges are not actually touching, and yet there is a force between them. And so those are called field forces. One that we're often or really familiar with is gravity. Gravity isn't actually touching you. You are in a gravitational field, Earth's gravitational field, and because of that, you are pulled down or towards the center of Earth. So that would be another example of a field force, a force that occurs without touching. So electromagnetic force, force between charged objects that pushes or pulls them. It is the result of a field force, and it can be attractive or repulsive. So what we wanted to look at is, we made some observations. How did distance affect the strength of the force acting on the bits of paper? And finally, why does the Tesla coil create sparks much farther from a metal object than the Van de Graaff generator? So really, I want you thinking, or hopefully recalling from your observations of the lab, that there were really two things that I could do to change the force. In other words, how much the arc that we got, that we saw, as well as how much it stung or kind of shocked us. And those two things are the distance as well as the charge, how charged up. The Tesla coil can generate a much larger charge than the Van de Graaff generator. And so what we find is that there is a relationship between not only charge or distance and charge and electric force. And so that relationship is distance, which we represent r, because we're talking about the distance between the center of the two charges. So distance r between the charges affects the strength of the electric charge. The closer they are, the more force there is. And the farther they are, the less force there is. And I think if we just think about this for a second, for distance, if I have two positive charges and they are really, really close to each other, then they're going to really, really push hard to get away from each other, because like charges repel each other. That being said, if I had two positive charges and they were 50 meters apart, they're barely going to push on each other at all because they're so far. So distance is an inverse relationship. So important to understand this. It is an inverse relationship. So as distance increases, force decreases. Charge, on the other hand, is a direct relationship. The larger the charge, the more force. And that's what we saw with the Tesla coil. The Tesla coil was able to build a really big charge, and therefore it could generate a really large force, literally pulling electrons towards it out of me or whoever, which caused a quite interesting sensation. So the larger the charge, and we need to should note charge strength is represented by Q, lowercase q. So the larger the charge, the more force. The smaller the charge, less force. So they are directly proportional. And I think hopefully this makes sense in that if I have two charges, let's say they're each 1 Coulomb, they're going to experience some attractive force towards each other. If I double them, so this is 2 coulombs and 2 coulombs, now they will be attracted to each other even more strongly because they have larger charges. And so we can summarize those things, or those things are summarized mathematically in Coulomb's law. So Coulomb's law tells us the magnitude of the electric force, so again this is F electric, is proportional, directly proportional, to the product, if you remember from math class, means multiply, right? The product of the two charges. So this is what's important. It's not just a single charge, it is the magnitude of both charges. So if I double one, that would increase it. If I double both, that would increase it even more. And so electric force is directly proportional to the product or multiplication of the two charges, of the magnitude of the two charges. So if I double one charge, the force would be doubled. If I half one of the charges, keeping the other one the same, the F electric would decrease by half. And so we would say something like, or we could write that as proportionality, F electric is proportional to charge 1 times charge 2. So now if I increase charge 1, F electric increases. If I increase charge 2, F electric increases. If I increase them both, F electric increases by the product of both of their increases. Distance, on the other hand, is an inverse, we already saw it is inversely proportional, but it is not just a simple inverse proportionality, it is inversely proportional to the square of the distance. So to write that out, we would say F electric is inversely proportional to, we use R here for distance, and not just inversely proportional to R, but inversely proportional to the square of R. Okay, and I think if we stop and think about that, let's just say R is 1. Well, so F electric would be proportional to 1 divided by 1 squared, so 1. Now if I double the distance, right, let's say that this is 1 meter apart, and then I make it 2 meters apart. So if I double it now, 1 over 2 squared, even though I'm doubling the distance, this force is going down by 1 over 2 squared, which is 4. So as I double distance, electric force is actually going down by 1/4. It is be 1/4 as much. Excuse me. If I tripled the distance, it would go down. It would be a 1/9, because 3 squared. You get the idea. If I quadrupled it, so changed it from 1 meter to 4 meters, now it would be 1/16. And so it's inversely proportional to the square of the distance. Okay, and then finally the last thing we need to understand is the direction of the force is dependent on whether it is attractive or repulsive. So opposite signs are attractive and the same sign is repulsive. And we kind of covered that on the previous slide, so just make sure you are aware. Opposite signs attract, same signs repel. Okay, so here's just kind of a little example. Could we rank these from which of these has the strongest repulsive force? So repulsive, well, let's see. These charges are opposite charges, so this is actually going to be attractive, isn't it? So we don't even actually want to consider these. These are the same charges, these are the same charges, and these are the same charges. Okay, so now we could think about which of these would have the greatest repulsive force, pushing away from each other. And so we know that it is inversely proportional to distance, so the less distance, the stronger. So this one looks like it has the least distance, but it is directly proportional to charge. So this one also has 2 times each of the charge. So this one is d away, and therefore, and compared to this one. So if we're just comparing pair 2 and pair 3, this one is going to be weaker because these charges are doubled and they have the same distance. So this one's out. So now it's down to these two. And since these have the same charges, 2, we can ignore the signs because they're both the same sign, so it would be repulsive in both cases. Since this is 2Q and this is 2Q, as well as down here, the charge is the same, but since this one has half the distance, less distance means more force, so pair 4 would actually experience the largest repulsive force because they have double the charges on each of their charges and half the distance. Okay, so now we can put that all mathematically. As we saw in our proportions before, F electric is proportional to charge 1 times charge 2. It is inversely proportional to the square of the distance between them. And then if we were to plug in numbers, we'd find that we were always off by some factor. And that factor is actually Coulomb, so a universal constant that is added to this equation, and that universal constant is called Coulomb's constant. It is written in long form here, but in reality, and this is on your equation sheet, we can just think of this as 8.99. So this 7 rounds the 8 to a 9, and we can just chop it off at 3 sig figs. So really, Coulomb's constant, we would say 8.99 times 10 to the 9th, newtons times meter squared over Coulomb squared. So this is Coulomb's constant, which goes in there as the same always. This is the charge of, the strength of charge 1. Again, its unit is Coulomb because that's how we measure the magnitude of a charge, or the unit for charge strength. Charge 2 would also be in coulombs. And then finally, this is the distance between them, and we would use the unit for distance, which is meters. So F electric is equal to Coulomb's constant times the magnitude of charge 1 times the magnitude of charge 2, all divided by the square of the distance between them. And if we look at our units here, I would end up with coulombs times coulombs over m meters squared. And so since Coulomb's constant is newtons times meters squared over Coulomb squared, my meters squared will cancel, my Coulomb squared will cancel with these two, and so the only unit I have left is newtons, which is good because since this is force, I want my unit to be newtons to indicate the magnitude of the force, electric force between these two objects, charged objects. All right, so just a quick kind of practice problem to work through that. It says, what is the electric force between a glass ball that has a charge of plus 2.5, so it is a positively charged object, times 10 to the negative 6 coulombs, and a rubber ball that has a charge of minus 5 times 10 to the negative 6 coulombs when they are separated by a distance of 5 centimeters. So it helps me to draw a picture, so we'll call this charge 1. Charge 1 is positive since it has a positive 2.5. So here's charge 1. Charge 2 is over here, and it has a negative value. So this is what we have, and then we know that there is some distance, the distance between their centers. And so the distance is 5 centimeters. Okay, so I can write this out, although I will need some more room. So Q1 is equal to 2.5 times 10 to the negative 6th coulombs. Charge 2 is equal to 5.0 times 10 to the negative 6th coulombs. And then the distance between them is equal to 5 centimeters. So if I look at the equation over here, I'm looking for the force between them. Coulomb's constant I always have. It's on my equation sheet and in my notes. They give me charge 1, 2.5. They give me charge 2, 5.0, and they give me distance. So it looks like, at face value, that I'm ready to solve this. But if we stop and think for a minute, you would realize that distance must be measured in meters. And they have given us our value in centimeters. So before I can solve this problem, I have to convert centimeters to the standard unit of distance in physics, which is meters. So I'm just using unit conversion, 100 centimeters in 1 meter. That cancels. So I end up with a distance between them of 0.05 meters. Okay, now it looks like I'm ready to solve. I'm going to need more room still. So the equation is F electric, which we're going to measure in newtons. So we want to end up in newtons. Oh, actually, let's go back for a second and just think through this. I've got a positive charge and a negative charge, right? Okay, so what direction will the force be? Well, these two will be attracted to each other, right? So the electric force will be, of each of them will be back towards the other. And so we saw before in our notes that if electric force is attractive, then it should have a negative value. So one way to check if our answer is right is, do we get a negative answer? Do we get a negative answer that has newtons as our only unit? If we can do those two things, then we're probably on the right track to getting this. So F electric is equal to Coulomb's constant, so 8.99 times 10 to the 9th newtons times meters squared over Coulomb squared, multiplied by charge 1, which is 2.5 times 10 to the negative 6th Coulomb, times charge 2, 5.0 times 10 to the negative 6th Coulomb, all divided by the distance between them squared, so 0.05 meters squared. Okay, so before I do any number crunching here, I actually made a mistake, didn't I? This charge 2, the magnitude of charge 2, it tells me is negative. I left it off here, which means I left it off down here as well. Good catch. And then let's double check that my units work out. So I've got meters squared. This square is going to distribute to both the 0.05 and the meters. So I'm going to end up with meters squared here, and that will cancel my meters squared and Coulomb's constant. Coulombs times coulombs is Coulomb squared, and I have Coulomb squared here, so those will all cancel. So it looks like I'm going to end up with only newtons as my unit, so that's good. And then finally I've got a positive times a negative, which means my value up top will be negative, which divided by a positive number on the bottom, which means my overall answer will be negative. So it looks like I'm going to get a negative electric force with newtons as the unit. So that would put me in pretty good shape. So let's see if I can not mess this up as I put it into my calculator. As I do, I'm going to put in 8.99, open parentheses, 8.99 EE to the 9th, close parentheses, open parentheses, 2.5 EE to the negative 6th, open parentheses, negative 5 E to the negative 6th. I'm going to hit enter there, because then I can not worry about like dividing it wrong accidentally, and I get negative 0.112375 newtons over 0.05 squared. So my electric force looks like it's going to be, I end up with, taking it to 3 sig figs, electric force is equal to negative 45.0 newtons. So what is the force between these two charged particles? About 45 newtons towards each other. And that negative tells me it is towards each other. So I hope this helped not only working through mathematically, but also understanding the concepts associated with electric force. Please double check your focus questions and make sure your notes are good. And as always, if you have any questions, check out the other resources or feel free to contact me and we can find a time to go over this. Take care.